Hi folks, in this video, we're going to look into the intuitions behind natural gradient learning. Natural gradient is a recurring concept within the context of stochastic optimization. And even though there have been many tutorials on this topic, many of them talk about things such as Riemann geometry and curvature, which in my opinion can be a bit unintuitive for beginners such as myself. So this video is intended to supply some of that missing intuitions. We're going to talk about the problem that natural gradient solves, what motivated its development, and in what ways is it better than just regular gradient. And let us begin by looking at the problem setting of natural gradient. What problem does natural gradient tries to solve? Well, the problem is known as stochastic optimization, and in this problem setting, we have an objective function f, whose value we're trying to maximize. But here's the stochastic part, because instead of controlling the input to this objective function directly, we control instead a distribution from which these inputs will be sampled. And this distribution is parameterized by some distribution parameters theta. And our goal here is to find theta such that our distribution is going to sample higher objective solutions on average. And to the right, I'm providing a simple toy example. So here our objective function is just a simple sphere function, where our goal is to try to minimize the distance, or in our case, maximize the negated distance, to the center of the sphere at 4, -4. In this particular example, the distribution that we have chosen is a multivariate Gaussian distribution, which means that our distribution parameters theta is going to consist of the mean of this Gaussian distribution and also its covariance matrix. The samples that are drawn from our multivariate Gaussian distribution are denoted as these yellow dots. And again, our goal is to update this multivariate Gaussian such that the samples drawn from it have higher objectives on average and therefore congregate around this optimum at 4, -4. And at this point, you might be wondering the motivation for this problem setting. Like, why do we have this distribution and why are we not optimizing the objective function deterministically? Well, in many real-world applications, such as controlling a robot, there's often going to be some noise to the control inputs that we supply. And having a distribution over the control inputs allows us to model that noise. So I guess you can say that very often stochastic optimization approximates the real-world problem better than deterministic optimization because of its ability to model the noise. And now that we know what stochastic optimization is, we can look at the first attempt of solving it. This is known as the evolution gradient, or search gradient, or in some cases policy gradient. And the idea is pretty straightforward. Because we're trying to maximize this expression over here by changing the distribution parameters theta, we're just simply going to differentiate this term with respect to theta, and that is going to give us this gradient over here. You don't have to understand how we derive this gradient, but just by looking at it, it should make sense, right? The overall idea here is that we take lambda samples from our current distribution, and for each of those samples, we're going to compute a gradient that essentially tells us how do we want to change the current distribution in order to make it more likely to sample that specific sample. So since we have lambda samples, we're going to have lambda such gradient, and then our overall gradient is essentially going to be a weighted average across all these samples. And crucially, the weight given to each sample, given to each gradient, is going to be the objective value of that sample. So that higher objective value samples are going to get their gradients scaled up more, and lower objective value samples are going to get their gradients scaled up less. So our overall update is going to make our distribution more likely to sample high objective samples and less likely to sample low objective samples. And when you actually derive this gradient over here, you're going to need to substitute into the PDF or probability density function of your distribution. We have a multivariate Gaussian here, so we're going to substitute the PDF of the multivariate Gaussian. And because in the case of multivariate Gaussian, the distribution parameters theta is going to consist of the mean vector m and the covariance matrix C, we're going to derive analytically this expression with respect to the mean vector and the covariance matrix each, and then we're going to essentially flatten each of those gradients and concatenate them in order to give us the long vector that will be our overall gradient. You don't have to actually understand any of these. This is just to give you a more concrete example about how this gradient will be derived analytically when you actually implement this algorithm. And for additional intuition, you can think of each sample as making a quote-unquote proposal that tries to pull the distribution closer towards itself. And in the case of multivariate Gaussian, pulling means two things. Firstly, each sample will try to pull the mean of the multivariate Gaussian closer towards itself. And secondly, each sample will try to stretch the covariance of the multivariate Gaussian such that the uncertainty is higher along the direction heading towards it. And although each sample is going to make a proposal, the overall update is going to weigh the merits of each proposal. And obviously, if a proposal corresponds to higher objective value, we want to favor it over another proposal that corresponds to a low objective value. So that was the overall idea. Now let us see an example of how this algorithm runs in practice. We can see that although this algorithm seems to be capable of adapting the distribution to the optimum, it tends to blow up right before it converges. Actually, the reason that this algorithm blows up is one of the key motivations behind natural gradient. So let's look a bit closer into this. As you can see here, the moment before it blows up, the distribution is actually kind of already well adapted. The mean of the distribution is located approximately at the 4, -4 optimum, and moreover, the covariance matrix is small. So overall, our distribution is sampling at the optimum with high precision, which is exactly what we want. So why does it still blow up? And if we rewind a bit, we can observe that right before the algorithm blows up, it makes this huge update on both the mean and the covariance, especially the covariance. And then it just kind of spirals out of control from there. This is where we make the observation that the gradients of a multivariate Gaussian distribution tends to be unstable when the current covariance is small. Now, the canonical way to explain this would be to show you the gradient update equations for both the mean and the covariance, which we would derive from here. And then you can observe that there is an inverse covariance term in both the mean gradient and the covariance gradient. And when the current covariance is small, this inverse term is going to scale up this xi minus m term, so any small variations in xi is going to reflect massively in the end gradient, hence why the gradients are unstable. But since I promised this would be intuitive, let us now look at some visual examples of what the gradients for both the mean and the covariance would look like in order to gain a better understanding on why the gradients are unstable. So first, let's look at the mean gradient. Here we have two distributions, one with small covariance and one with large covariance. And we're trying to maximize their respective likelihoods of sampling this target xi by only changing the mean. And our question is, how should we update their means respectively in order to maximize their target likelihood? Well, in this first distribution, in which the current covariance is small, our mean update has to set the mean of the distribution exactly at xi. Because we're sampling with high precision, and the mean kind of controls whether we're sampling at the right location with high precision or the wrong location with high precision. And in the former case, we're going to get very high likelihood, and in the latter case, we're going to get very low likelihood. So it's kind of like all or nothing when the current covariance is small. But by comparison, when the current covariance is large, we don't necessarily have to set the mean exactly at xi, because we are already kind of sampling all over the place. So even if we set the mean exactly at xi, our likelihood of sampling it is not going to be particularly high. But on the other hand, even if we set the mean slightly off, like it's not the end of the world because we're so imprecise and some of the samples are probably going to land on xi. So compared to the low covariance case, in which our update is like all or nothing, in the large covariance case, our updates are more fuzzy. And we observe similar trends with the covariance gradients as well. In this example, we again are trying to maximize the likelihood of sampling this target xi, but this time, instead of allowing only the mean to change, we allow only the covariance to change while keeping the mean constant. So the question again is, how do we want to update the covariances of this small covariance distribution and this large covariance distribution in order to make them more likely to sample xi? Well, in this first example, in which the current covariance is small, we are sampling at the wrong location with high precision, so our current likelihood of sampling xi is extremely low. And because we are only allowed to update the covariance, the best we can do is to actually increase the sample uncertainty along the direction heading towards xi. So we allow the distribution to sample some distance from the mean, but only along the direction heading towards the target. And this, in effect, is going to stretch our covariance very thin, giving us something that looks almost like a straight line. And by comparison, when the current covariance is large, because we are sampling with low precision, like sampling at the wrong location is not as catastrophic as when we had small covariance and high precision. So we are not as hard pressed to make a huge update on the covariance because we can already sample xi with some reasonable likelihood. So we can conclude that overall, gradients are sharper when the current covariance is small, in the sense that we make large updates in order to get high likelihoods on the targets. And by comparison, when the current covariance is large, the gradients are more fuzzy in the sense that we don't make as large updates, but then we don't get as high likelihoods on the targets either. And then you might remember our earlier analogy about each sample taken from the current distribution, making a proposal that pulls the distribution towards itself. When the current covariance is small, each of those proposals is going to pull a lot harder. And it's very easy for some of them to pull a bit harder than the others, and then the overall gradient just swings massively in favor towards those proposals, giving us an overblown gradient. And in order to make the gradient updates less susceptible to blowing up, we want to somehow tune down the gradient update when the gradients are unstable, which brings us to natural gradient. The high-level idea here is that we want to compute the variance across the gradients at each xi, and then we divide the overall gradient by that variance. So when the gradients are unstable, the variance is going to be high because, as we just saw, they change a lot across each xi, and thus the discounted gradient is going to compensate for that instability because it is divided by a larger term. And of course, although I've been saying variance as if it were univariate calculus, we're talking about multivariate calculus here, so the variance should really be covariance, which is given by this expression over here. This is just the definition for covariance after substituting the gradients. And notice because this term here, which kind of corresponds to the mean gradient across all xi, is 0. This is because the Gaussian distribution is a symmetrical distribution. The overall expression simplifies to this, and this is known as the Fisher information matrix. And then given this Fisher information matrix as a measure of covariance of gradients, and by extension the instability of gradients, we are going to pre-multiply the original gradient by the inverse of this Fisher information matrix. And this discounted gradient, after pre-multiplying with Fisher, is known as the natural gradient. And this is more stable than the original non-discounted version because, again, it is going to receive a large discount when the gradients are unstable. Now, you may have noticed that the main complexity with a natural gradient is actually the computation of Fisher information matrix. So let us see an example of how this can be done. Well, in our case, because we are already computing this gradient at every sample, we can use the samples to empirically estimate a Fisher information matrix every time we need to make a gradient update. So at each sample, we're going to compute the gradient with respect to the mean and also with respect to the covariance matrix at this sample. And then we're going to flatten and concatenate them into a long vector. And then as the equation here specifies, we're going to take the outer product of this long vector with itself. And this is going to give us one matrix for this one sample. And then we are going to repeat this process for the next sample and also yet more samples. And in the end, because we have lambda such samples, we're going to have lambda such matrices. And our empirical estimate of the Fisher information matrix essentially comes down to taking the element-wise average across all these lambda matrices. And as we just mentioned, because we are estimating the Fisher information matrix from our samples, we are calculating an empirical Fisher information matrix. And alternatively, you can also derive the Fisher information matrix analytically to have an expression that's just going to give you the Fisher information matrix. I think this is doable for multivariate Gaussian distribution, even though we are not showing that in this tutorial. And with that, we conclude our very much surface level tutorial on natural gradient. And as a quick recap, natural gradient solves the stochastic optimization problem, where we're trying to update a distribution to make it more likely to sample high objective samples. And then we saw a simple first attempt algorithm which takes the gradient of the expectation of the objective function with respect to distribution parameters theta. Quite a tongue twister, I know. But anywho, then we observed that this gradient tended to be unstable when the covariance was small. And the way we addressed that was by quote-unquote dividing the gradient by its covariance such that it is tuned down when it is unstable. I should quickly note that even though in this tutorial we've been using multivariate Gaussian distribution as an example, natural gradient is not restricted to multivariate Gaussian. But if you switch to a different distribution, this motivation part may no longer be illustrative because you may no longer be working with a covariance matrix. But the overall argument still holds. There will be some regions in which the gradient is unstable, and natural gradient allows us to account for that. So now let's see a demo of how this algorithm runs. As you can see, this is clearly better than the first attempt because it was bold when it needed to at the start of the optimization when it's still far from the optimum. But once it starts to converge, it becomes more cautious and therefore it's much more stable than evolution gradient. So yeah, that's it. I certainly encourage you to look up more elaborate tutorials on natural gradient, and I hope this video helped with your intuitions. And thanks for watching.